sedimentary processes you want to date. There's multiple techniques, multiple chronometric systems available to us. And so you need to be careful in what you choose, which will best answer the questions you're trying to address. And then I walked you through some of the step-by-step procedures that in general you should go through for whichever chronometric system and technique you choose, starting with defining your problem, making sure you have the field relationships nailed down as best you can, how careful you should be with collecting samples to minimize cross-contamination issues, the preparation of the sample before you actually get to the lab itself, wherever that lab may be, and that may involve standard crushing, grinding, and mineral separation techniques, or it could be in situ techniques. And that part of that decision of which technique you use and which chronometric system you use comes down to this balance between accuracy and precision. So precision, that's great. That's going to give you small errors. But if it's not providing accurate ages for the relationships you're trying to constrain as far as their timing is concerned, then precision is not the most important aspect. It's the accuracy of your ages that's most important, and then precision is what you want to have as best you can, but it's not the defining factor as far as what's most important. Most importantly, you want to have accuracy, and then you want to use the techniques in the chronometric system that provides the most precision, but it's still giving you the accuracy you need to answer your question regarding the timing of a shear zone, a structure, metamorphic event, what have you. And then I continued with how we go about from the sample preparation and doing the analyses to the actual acquisition of the data reduction. And you'll have started that in your labs, looking at some data that's provided for you that you put into a spreadsheet and you plot with an isoplot, or you plot it manually. You should get reasonably the same answer in both using both techniques. And now I would like to focus a little bit of time here on what's called the closure temperature, because we need to be mindful of this depending on which chronometric system, uranium, lead, argon, uranium, thorium, helium, apatite fission track, zircon fission track, whichever system you happen to choose, you need to be mindful that some of these isotopic systems do become open systems if the temperature is high enough. And in a way, this is problematic because if you don't properly account for that temperature and possible open system problem, you can get some very misleading ages. On the other hand, the closure temperature for a given mineral, which I'll cover in more detail in a moment, can also provide for us a very powerful technique for constraining the time at which rocks have been exhuming through different parts of the crust and cooling through different temperatures or isotherms within the crustal section. And so that can be very powerful with regard to the timing of shear zones, especially extensional shear zones, and trying to constrain rates of exhumation, rates of cooling. I'm not going to be able to get into all of the nitty-gritty details of it. There's a lot of complexity in it, but I'll provide for you a first-order pass at what's involved in acquiring ages that have a closure temperature attached to them, and how we can use that to provide for us some ideas about rates of exhumation, rates of cooling within a given tectonic environment. So the concept of closure temperature has been bandied around pretty much since the start of geochronology, in that we know that for a given mineral, for a given isotopic system, that if you raise the temperature high enough, there is a volume diffusion, a temperature activated volume diffusion that occurs within a mineral. And this concept also applies to metamorphic petrology and igneous petrology as well, in that we can look at the diffusion of different elements within a mineral and begin to use that and their rate of diffusion and the kinetics that are attached to it to start to get things like pressure and temperature estimates. But we can also use that same concept when it comes to the diffusion of either the radiogenic parent within a given mineral or its stable daughter product. In either scenario, if the parent or daughter is diffusing in or out of the mineral, that means you are not in a closed system, for which the age equation, that is a major underlying assumption, that it's a closed system. And so you need to account for this possibility that the temperature may have been high enough to allow volume diffusion to occur. And so this was really first quantified by Dodson in 1973. It's referred to as closure temperature, or annotated as TC. And this assumes that at the time the closure temperature is attained, little or none of the daughter product is retained at temperatures above the closure temperature. And once the temperature attached to a measured radiometric age, if we know what that closure temperature for the mineral is, we can say, well, the age we get is reflecting the time at which that mineral, that rock, passed through the isotherm in the crust that is the closure temperature for that particular mineral, which means at that point in time, it became a closed system, and the radiogenic daughter product that's accumulating is not diffusing out. It's being trapped within the mineral rather than diffusing out. And so the closure temperature gives us the time at which that mineral, that rock, that part of the crust passed through an isotherm, at which time the mineral became a closed system for its parent and, importantly, the radiogenic daughter product, such as lead for uranium lead, as an example. The closure temperature can be calculated using Dodson's equation, which I show down here in equation 1. I'm not going to get into all aspects of it, but there's some constants, like E here is the activation energy, R is the gas constant, TC, this is what we want to get at eventually within the equation. That's the closure temperature itself. DO is the diffusion coefficient, R is the radius of the mineral, and DT, capital T over DT, small t, that is the cooling rate. And so some of these are constants, the activation energy, the gas constant, but some of them vary, such as the cooling rate and the radius. And so two of the most important factors within this Dodson equation for closure temperature are the cooling rate, here dT over dt, and the effective diffusion radius, R here, or R squared. And so knowing the cooling rate, knowing the effective diffusion radius, we can very accurately calculate the closure temperature. The problem is it's very difficult most times to actually get a handle on precisely on what the cooling rate was. And also the effective diffusion radius can be quite different from one mineral to another, or within the same mineral species, such as zircon. You could have many different sizes and shapes of zircon, and therefore you have to, or any other mineral that you're dealing with, and therefore you have to calculate a closure temperature perhaps more than one for different sizes and different shapes of zircon or other minerals that you're trying to date. Eventually, what we usually have is a mean value for the closure temperature for that particular mineral. Let's say we're dealing with zircon and we calculate what its closure temperature is based on all of these different factors, including knowing what the cooling rate is and its effective diffusion radius. We are assuming that this closure temperature is the same throughout the actual mineral, individual mineral itself, but it actually varies based on the crystal structure itself. There's certain pathways within the crystal where the diffusion might be faster or it might be slower. Also, the closure temperature is typically lower near the surface boundary of the mineral, and that is mainly because there's often pathways near that surface boundary created by damage due to the fission of the parent product creating what's called recoil, which damages the crystal structure, and these can create fast pathways for diffusion. Also, the radius of diffusion nearest the boundary is very small compared to the radius of diffusion from the center of the mineral. So the closure temperature in reality actually varies throughout the crystal. It's not constant even in a single crystal, let alone a whole population of crystals, or in a rock that you're dealing with in a panel of the crust that you want to try and get a closure temperature for. So these are some things you have to take into account. It's not as cut and dry as one might think given this Dodson's equation.
Dan?
Yeah.
I have a quick question. You mentioned that the equation is based on the cooling rate. Now, very often the cooling rate is determined with geochronometers themselves. So how can you independently, I guess, determine the cooling rate of a given system without going into a circular argument?
Right. Great question, Laurent. And that is something that people, geochronologists especially, grapple with, and it does become somewhat of a circular argument, or at least an iterative argument, in that as you adjust that cooling rate, because you've got chronometers that are used to constrain that cooling rate, you can, for certain chronometers like zircon and monazite, the closure temperature is so high that there's usually the geologically meaningful temperatures never reach that temperature at which zircon and monazite become an open system, at least as far as volume diffusion is concerned. And so you can use those ages that are not really affected by a closure temperature that is a geologically meaningful temperature to begin with, to constrain one end. At the other end, you may have some information that you know that there's an unconformity or a volcanic sequence that suggests that you were at surface at a particular time. And so you can constrain those two endpoints and then infer what at least the minimum cooling rate must have been. So you can see here that there's big assumptions that get layered into this equation, and that's what makes it so difficult to really nail down the closure temperature for an individual mineral, let alone one that's, or let alone a number of minerals that you might use to get the temperature at which that crustal panel you're dealing with cooled through various isograds on its way up to the surface. So long story short, that's probably the most problematic part of the Dodson equation, is getting that cooling rate, and a cooling rate that's actually realistic and reflects what actually happened to that exhuming panel of rock. Okay, so let's just assume for the time being that we can reasonably calculate the closure temperature of various minerals using a few different chronometric or isotopic systems. The power of using the concept of closure temperature, if you can reasonably estimate for a given mineral in a given isotopic system what the closure temperature was, you can then begin to constrain the time at which this rock or panel of the crust was exhuming through higher and higher levels of the crust and passing through the isotherm that represents the temperature of the closure temperature of a given mineral and isotopic system. And so in theory, if you were to say take a rock and you separated out some zircon and monazite, or you did in situ analyses, and you were able to constrain it to 100 million years ago. So 100 million years ago, those rocks, those minerals within the rock they crystallized and began to accumulate their stable radiogenic daughter product. So these would be your high temperature minerals. And then perhaps you choose other minerals that have closure temperatures that are at a lower temperature, progressively lower temperatures, like amphibole perhaps is around 400, 450 degrees, maybe up to 500, depending on how big it is and the cooling rate. Muscovite perhaps is around 350. Biotite, the argon-argon system, closes at around 250, 300. You can see big error bars here, of course, for the temperature on the x-axis. Cape Feldspar for argon-argon, it's between, say, 200 and 250 to 300. And then into the fission track, zircon and apatite, and also the uranium, thorium, helium systems for zircon and apatite, which are, for isotopic systems, some of the lowest closure temperatures, and therefore can give you the time at which these rocks pass through the uppermost part of the crust, say in the upper 5 or less kilometers of the crust, depending on what the geothermal gradient is, of course, for that part of the crust, which in itself is very difficult to establish sometimes. And so here on the right-hand side of the diagram is a schematic overview of, when these different minerals in their isotopic systems, uranium, lead, thorium, lead, and monazite and zircon, that's going to give you your highest the time of highest temperature timing. And then as you come up through, you have hornblende and muscovite and biotite that are based on the argon-argon system that I'll talk about in case study 3. And then the lowest temperature ones, the zircon and apatite fission track and uranium, thorium, helium systems that show you you're getting, or the rock was in the upper part of the crust near the surface at the time these closure temperatures were attained. And so this application of these different isotopic systems and minerals with different closure temperatures, this is referred to as thermochronology, and it effectively provides for you timing constraints for the exhumation of a panel of rocks through the crust through time. And then that can be related to either cooling rate and or rate of exhumation. And so in this next slide here, I show a schematic overview of the Okanagan Valley Fault System in southern BC. It's one of the big fault systems that removed a substantial part of the upper crust and exposed or exhumed deep levels of the metamorphic infrastructure of the Canadian Cordillera in southern BC. And using uranium lead geochronology for zircon and monazite, as well as dating of the deformation, the shear zone fabrics and deformed and undeformed dikes within the shear zone, we were able to say that that shear zone was active at a depth of around 20 to 25 kilometers at 55 million years ago. So in this second panel, the middle panel here, this is the Okanagan Valley shear zone that we can see separating the hanging wall rocks of low metamorphic grade from the footwall rocks that are exhuming from deeper depths that were initially at 20 to 25 kilometers depth. And then using argon-argon isotopic system within amphibole, hornblende, muscovite, and biotite, and also some apatite zircon fission track data, we know that these footwall rocks that were at 20-25 kilometers depth were pretty much at the surface by 50 million years ago. And so this gives us a ballpark estimate for the rate of exhumation of about 4 to 5 kilometers per million years. And so this is an example of how, using the concept of closure temperature, although it can be problematic to ascertain what the actual closure temperature is for a given mineral in a given environment, it can still be quite helpful in understanding the deformation processes, the timing or rate of exhumation in a given terrain. And so that's, apart from being problematic, it can also be quite powerful in providing information to us that allows us to better reconstruct that exhumation history of a given terrain. Okay. At this point, I'm going to move on and I'm going to look at a couple case studies just so you can see how you can use these different techniques and isotopic systems and apply it to real structural tectonic problems. Also, I'm going to highlight some of the drawbacks and some of the pitfalls that you might run into when applying these different systems. So I'm going to move on to the next PowerPoint lecture, the next PDF for you. That's referred to as case studies 1, 2, and 3. Oops, sorry, that's not the one I was looking for. Okay, is everybody with me? Yeah?
Yes.
All right.
Yeah, I'm with you.
Okay, great.
Yes.
So I'm going to now, awesome. I'm going to now look at a few case studies if we have time, at least 2 of them. I might skip the one that involves my own data. But what I'm going to look at is using a few different techniques and different isotopic systems in old and young origins and in hot and cold shear zones to give you an idea of how we can apply these techniques in different ways to get at answers that are best suited for the problems we're addressing for a given environment. So I'm going to start looking at an example from the Western Churchill province here. It's in the heart of the Canadian Shield in northernmost Saskatchewan and southeastern Northwest Territories. Within this belt of rocks called the Snowbird Tectonic Zone that separates out the Archean Ray province from the Archean Hearn province here in green. And I'm going to focus in on this box here, on this little pink triangle that's referred to as the Tintado domain, or some others call it the East Athabasca Mylonite Triangle. It's partly overlain by the Athabasca Basin in northernmost Saskatchewan. And I'm going to focus on how, using some clever manipulations of the techniques that I've talked about and the different radiometric systems available to us, they were able to refine our understanding of the timing of a couple different shear zones in this region. And so we're going to look at, in this first case study, the application of geochronology to high temperature deformation and providing age constraints for that deformation, in this case for Paleoproterozoic deformation. And so in the diagram here, we can see in the blues, this is the ray domain, and it was largely metamorphosed to upper amphibolite and granulite facies metamorphism. You can see here very high pressures of 0.9 to 1 gigapascal, 800 to 900 degrees Celsius, so quite deep, quite hot rocks that are now at the surface. And they were deformed and metamorphosed at least twice, once at 2.6 billion years ago and once at 1.9 billion years ago. And on the other side here is the Hearn domain, much lower pressure rocks, 0.5 gigapascals, and only 600 to 650 degrees Celsius. These two major crustal panels, the Hearn domain and the ray domain, are separated by a couple big shear zones. One's called the Grease River Strait River shear zone in gray here. It's a transpressional dextral strike slip shear zone, and the other one here in darker gray with the little black triangles on it, that's the Lakes Lake shear zone. And we're going to focus in on this panel of rocks here that is in the triangle between the Grease River Strait River shear zone and the Lakes Lake shear zone. But mainly, we're going to look at how age constraints were provided for these two different shear zones. The first thing you can note, though, is that from a relative timing context, the Grease River Strait River shear zone appears to cross-cut and offset the Lakes Lake shear zone. So the age constraints we should expect to get for those two significant shear zones, Lakes Lake should be older, Grease River Strait River should be younger. Prior to this study that was undertaken by Mike Williams and his graduate students at the University of Massachusetts, the timing on these structures was actually thought to be 2.6 billion years ago, but that was based on some really old geochronology that was acquired back in the late 70s and early 80s. And so at the University of Massachusetts, they used one of the techniques that I briefly mentioned, the electron microprobe, and they used this. It's a very powerful technique in that spatially you can get down to less than a micron. You can date domains within a mineral that are less than a micron big, and you can do it in situ. The drawback is the precision is not nearly as good as other in situ techniques such as sensitive high resolution ion microprobes or the shrimp or laser ablation ICPMS. But the spatial precision is the best amongst the techniques that are available. And it became quite popular using microprobes to get age constraints back in the late 90s and early 2000s because most departments had a microprobe available, and so they thought as long as they could measure uranium and lead, they could get ages. And it turns out that it's a lot more complicated than what people first thought it might be. The basic idea is that through the accumulation of the stable lead daughter products of thorium and uranium, you can calculate the time for the total accumulation of all the radiogenic lead within a given mineral, such as monazite or zircon. And knowing the decay constants for thorium and the two uranium radiogenic isotopes, 235 uranium and 238 uranium, you can use this transcendental equation here, where the asterisk lead here is the total accumulation of radiogenic lead due to thorium-232, uranium-238, and uranium-235. And this factor T in each of the exponents here, this is the time. And so it's an iterative equation. You keep plugging in different times for T. Computers can do it almost instantaneously. So as long as you can measure the radiogenic lead, the parent thorium, uranium, and their concentrations, you can, in theory, get T. One issue right away is that there is always common lead, especially within monazite, and that common lead is the amount of initial lead incorporated into the crystal at the time that that mineral crystallized. And so you need to extract or remove that component of common lead to calculate the actual radiogenic lead. The problem is with electron microprobes, you cannot do this. And so there's an implicit assumption made that all of the lead is radiogenic lead, radiogenically derived lead from the parents, and no incorporation of common lead. For really old Proterozoic and Archean minerals such as zircon monazite, that's not a problem because the amount of radiogenic lead would be so much greater than the actual common lead incorporated that the common lead makes virtually no difference in the overall lead budget. And so this technique, the electron microprobe technique, I would say is only something that you might consider applying for really old Proterozoic or Archean rocks or shear zones. So to go about doing this, there's some procedures that they published, Williams and Jersinovic, detailing how you might go about using the electron microprobe. I'm not going to go into these in great detail, but a few of the procedures, the steps that they take here that they published, this can be applied for just about any in situ analyses, especially within thin sections, that for different techniques such as shrimp, laser ablation, or other ion microprobes. And so the first thing they do is they create a full section map using one of the major elements within that rock type. Maybe it's magnesium or calcium or iron, something that creates a full section map for you using the electron microprobe. This is done by an automated process with newer microprobes these days. The next thing they do is they process maps for the accessory mineral that you're interested in. In their case, it was monazite. And so you select a trace element within monazite, such as cerium or yttrium, and you can then map your thin section for that particular trace element, and you will see little bright spots in your map in amongst just a complete field of darkness. And those little bright spots we'll see in a moment represent the locations, all the locations for that monazite or zircon or whatever mineral you're interested in. And then you select the mineral such as monazite that you want to analyze and try and get a age constraint from. You strategically select them based on where they are situated within the thin section. So maybe there's a fabric in which the monazite or zircon grew within, or it's in a texturally important domain, such as in a garnet pressure shadow, or within encased within a garnet itself, and you can constrain when the garnet must have grown. So you choose your mineral strategically based on what you're trying to address, whether it's timing constraints for fabric development or timing constraints for metamorphic pressures and temperatures. And then the next thing they do is generate age maps. This is specific to electron microprobes. I'm not going to get into that in too much detail, but I will show you an interesting little enigma that they solved using age maps. And the last thing that I would cover here is the calculation of the ages. I won't go through steps 5 through 9. This is more of a protocol for electron microprobes that we don't need to get into at this point. So, as I said, this step 1, the acquisition of a reference map. In this case, it's magnesium, and it's for a metapelite, a metamorphosed mudstone. But in this case, it was metamorphosed to very high pressures and temperatures. And this big gray area, that's a garnet, and then these lighter looking minerals here, these are biotite. And then there's quartz and feldspar that are the black areas, and some cordierite as well. And so you get your base map, essentially, for your whole thin section. And then the next thing you do, in this case, they mapped the same thin section for cerium. And I don't know if you can see it, but take my word for it, there's little wee bright spots within this field of darkness here. And all of those little bright spots represent locations of monazite. And so then they just overlaid, so it's much easier to see where these monazite were, little yellow dots that represent the locations of monazite. Sometimes you can use different shades of this color or bigger and smaller dots to indicate ranges of sizes. There's all sorts of things you can do to refine these maps. And then the next thing they did was superimpose those yellow dots back onto that base map that they created with magnesium. And this highlights within that thin section all the locations of the mineral of interest for dating purposes. In this case, it was monazite. I can't tell you how much of a step forward this has been for us. Identifying all the locations of monazite or zircon or whatever radiometric mineral you're interested in is extremely powerful. In the past, we had to do this optically using a microscope, and it was painful, and very often it was inconclusive whether you're looking at monazite or apatite or zircon, because they were so small you couldn't do any optic axis figures on it, and so it became a real head scratcher whether or not you were actually looking at monazite or zircon, and therefore debate as to whether you should waste an analysis on that particular mineral that may or may not be the radiogenic mineral you want to analyze. And so this was a big step forward in that we could find all of the accessory minerals, the radiogenic accessory mineral like monazite, and their locations, and then strategically pick which ones may be encased in garnet here, or maybe in a garnet pressure shadow, or maybe in this shear band within the outside the pressure shadow of garnet, to try and get some age constraints for different features within that thin section. And doing that in situ was a big step forward as well, whereas before you might have to crush and grind and separate out all these minerals and lose all of that textural and fabric information associated with the mineral that you wanted to date. One of the beauties of, I love monazite, it's one of my favorite minerals, and so these are different thorium and yttrium maps, chemical maps of the monazite. So perhaps you've selected a few monazite from this thin section here, and the next thing you would do is you would actually individually chemically map the monazite. Usually, in this case for monazite, we do thorium, yttrium, uranium, perhaps calcium. And what became very clear was that monazite can actually be a fabric-forming mineral. That's so powerful when it comes to dating shear zones, because dissolution reprecipitation domains in monazite can often be correlated with the finite strain ellipse that is correlatable to the shear zone that you're dealing with. And so if you can identify through your chemical mapping, these reprecipitation domains, and you can then correlate them with fabric development, then that is a powerful way to constrain the age of a given shear zone, as long as monazite grew within that shear zone. The same can be done with zircon as well. but it's not quite as common to find reprecipitation of zircon like you do with monazite. So this was something, or one of the reasons why the UMass people focused on monazite, because they quickly found, as they were monkeying around with mapping, chemically mapping monazite, that it was very commonly a part of the fabric forming mineral paragenesis. And so ideally you want to date these reprecipitation domains as well as the interior cores. And here's an example here of some of the chemical maps of a given monazite. You can see here, depending on which chemical thorium here, uranium, lead, yttrium, you get a different perspective of what the internal zonation, chemical zonation is of that mineral. And it became quite clear to them and to most other people who were dealing with monazite, and I was a graduate student at the time, that dissolving a whole monazite like we were doing previously was a big problem, because you can see here, if any of these chemical domains represent domains of recrystallization at different times within the monazite, you're basically averaging out all of these various age domains in a monazite. And same can be said for zircon and for bedelite and titanite, other radiometric minerals as well. And so it became clear that unless you were careful and you identified these chemical domains that are possible age domains, you may be erroneously acquiring age constraints that are a combination of more than one age domain within a single mineral. And just think, back in the day, we used to do multi-mineral analyses where we would dissolve 5 or 10 monazite or 5 or 10 zircon. So the problem gets amplified even more when you do multi-crystal analyses. So this was very insightful, getting these chemical maps and seeing that a mineral like monazite or zircon can have these chemical domains that may or may not equate to age, different domains or different ages of recrystallization. This is what's referred to as an age map. I'm not going to get into it too much, but using their electron microprobe technique, the Williams research group, what they did for each pixel you see in this monazite age map, each pixel represents effectively a different date or a different age. It's not precise at all, but each pixel represents an analysis where they analyze for uranium, thorium, lead, and yttrium, and they plug that into that transcendental equation I showed previously. And for each and every pixel, that represents a different age. You can't really use this to acquire age constraints because the precision is very low. So your errors are huge, but what it does for you, this age map, it actually shows you very accurately where you have different ages of recrystallization within the monazite. So you can see here a rim that's much apparently younger, and a core within the monazite that's quite a bit older. And what I'd like to highlight as well, this is that enigma that they managed to solve using this age map, is this little band of slightly off-colored orange, yellow, that's slightly off-color to a purplish band here. This represents an annealed fracture within the monazite. And it basically what's happened is, as that fracture annealed, you get an averaging out or a combining of the uranium-lead isotopic system, such that you now have some very different age that has no geologic meaning to it, because it's an altered age, an altered isotopic system for uranium, thorium, and lead. And that was quite instructive, because in backscatter electron imaging, you could not see that fracture. That was not apparent in backscatter. It was only apparent in this age map. And so using that age map, then they went into these individual domains, the older domain and the younger domain, and then they did much higher precision analyses within those domains. You could also take this map and use a shrimp or use laser ablation, a couple other different higher precision in situ techniques, and do the same thing, put down a number of spot analyses within a given identified domain. And then you can combine those analyses and take a weighted mean of those analyses to give you a reasonably precise age for these domains. So the interior domain, it's around 2,500 million years old, and the rim around it is around 1,811 million years old. So very different ages. One's Archean, one is Paleoproterozoic, and that was, only available to us because of the chemical mapping and the in situ analyses that had high spatial resolution. And then you can take a population of monazite, say within that thin section, and you're pretty sure that the rims on the monazite represent a given event or age of recrystallization, and combine those to further refine your precision, your error for that particular domain. And they found that it was around 1,829 plus or minus 9 million years old for this external domain, which becomes very important as far as correlating with timing of the movement on one of the shear zones that we'll look at in a moment. Okay, so coming back to the map here, and we're going to focus in on the Legs Lake shear zone. Here. And look at how timing constraints were provided for the Legs Lake shear zone when that was active, which brought up this high pressure, high temperature panel of rocks over top of this lower pressure, lower temperature panel of rocks within the Hearn domain. And so one of the key thin sections, S32D, doesn't matter what it's named, it could be number 1 for all that matters here. What they did, again, they did the full section magnesium reference map, identified where all the monazite were, and then chose a number of the monazite that were in textural and fabric, important domains of textural and fabric relationships. And they found that a number of the monazite here have a low yttrium core surrounded by high yttrium rims, and that's related to garnet growth and garnet breakdown, because garnet is a metamorphic mineral that takes in a lot of yttrium. And so if garnet has grown, there's not much yttrium available, leading to relatively low yttrium domains in monazite. And if garnet is breaking down and releasing yttrium into the effective bulk rock composition, then you get growth of high yttrium domains. And so then you can begin to correlate not only these reprecipitation domains with fabrics, but you can also correlate it with major metamorphic reactions that may have been going on during the development of that fabric. In this case, the breakdown of garnet, meaning that you must have been exhuming along this contractional structure that Legs Lake shear zone. So something was going on to remove the crust above that was leading to decompression in the breakdown of garnet. And so looking at this yttrium map here in the lower left panel, we can see that there is at least 2 Archean domains that were identified, this low yttrium one at 2488 and the high yttrium one right in the core of the monazite at 2518. And so overall, it looks like if you look in the lower right panel here at the age map, that core of the monazite is around 2,500 million years old. That's the time that they have ascribed to the high pressure, high temperature metamorphism and deformation within that ray domain, within the hanging wall block of the Legs Lake shear zone. And then the rim domain, a combined analysis of a number of monazite from that sample provided an age of 1829 plus or minus 9 MA. And they ascribed that particular time to when the Lakes Lake Shear Zone was active, and there was uplifting of the deep crust within the ray domain that was being uplifted on top of the Hearn domain to the east. But there must have also been significant exhumation, something that was removing the material within the hanging wall block as it was being uplifted. Something that still hasn't been resolved is what was the, was it just erosion, or was it some extensional structures higher in the crust removing that material in the uplifting hanging wall block? That hasn't been reconciled yet. And so what they are able to show in this block diagram here, this is the ray domain here in the hanging wall. Here's the Hearn domain in the footwall. Here's in gray here, the boundary separating the two is the Lakes Lake Shear Zone. And so you're bringing up 1 gigapascal rocks, or rocks from 1 gigapascal very deep within the crust, 35, 40 kilometers depth in the crust, over top of rocks that were in the mid-crust, perhaps on the order of 15 kilometers depth. And so that Lakes Lake Shear Zone that facilitated the uplift of the ray domain appears to have been active primarily at 1.83 billion years ago. Now we'll focus on the Grease River, Straight River Shear Zone and how timing constraints were provided for that. So here is a beautiful quartz myelinite that we can see. We'll focus in on this little beauty here. That was a monazite that they identified within the quartz-rich myelinite, and they found that this monazite, for the myelinite taken from the Grease River, Straight River Shear Zone, had these beautiful reprecipitation, high yttrium reprecipitation domains that they were fairly confidently correlating with the extensional domains of the finite strain ellipsoid for the Grease River, Straight River Shear Zone. And so by dating those reprecipitation domains, that gives some confidence for timing constraints when that Grease River Shear Zone was active. And what they found was that those reprecipitation domains are somewhat younger in age than those found for the Lakes Lake Shear Zone, in that it was around 1809 MA versus the 1830 MA for the Lakes Lake Shear Zone. And so here is a schematic evolution in time here for the snowbird tectonic zone. So at 1.83, there was major contractional movement on the Lakes Lake Shear Zone with a minor component of dextral displacement that was bringing this blue ray domain over top of the Hearn domain. And then at 1.8, around 30 million years later, the Grease River, Straight River Shear Zone was active, and that displaced in a right lateral sense the Lakes Lake Shear Zone, creating these sort of lozenge or rhombic patterns for the offset parts of the Lakes Lake Shear Zone and its hanging wall, high pressure, high temperature domains within the Ray province. Okay, so how about we take a 5-minute break here, and I'll come back. I'm going to skip over the area in the northern Selkirk Mountains because you're looking at that anyways for your lab. But I'm going to look at a low temperature shear zone within the Canadian thrust and fold belt, Canadian Cordilleran thrust and fold belt, and how timing constraints have been provided for those faults. So we'll come back in about 5 minutes and take a look at that.
Okay. Thank you, Dan.
Everything was crosscut this way.
I wonder where replying.
Yeah, I don't know. I'll shoot him a message, see where he is. The illness is going well. I was hoping to have